Let's talk about the standard basis in R2 and R3, the basis that we're accustomed to. So if I take R2, I can have a basis 1, 0, that's one vector, and the other vector is 0, 1, okay? Also known as I and J, also known as E1 and E2. Again, just different symbols for the same thing. R3 is the same thing. R3, we have 1, 0, 0, 0, 1, 0, and 0, 0, 1 as a basis. Three vectors, three-dimensional vector space. You also know them as I, J, K, and we've also referred to them as E1, E2, E3. Now, what's interesting about these particular bases, notice, let's just deal with R3. Vector 1 and vector 2 are orthogonal, meaning their dot product is 0, perpendicular. 1 and 3 are orthogonal, 2 and 3 are orthogonal. Not only that, they're not just orthogonal, mutually orthogonal, but each of these has a length of 1. So that's what we call orthonormal, that the vectors are mutually orthogonal and they have a length of 1. As it turns out, this so-called natural basis works out really, really well computationally. So we want to find a procedure. Is there a way where, given some random basis or several random bases, can we choose among them and turn that basis into something that is orthonormal, where all of the vectors have a length of 1 and all of the vectors are mutually orthogonal? And as it turns out, there is. The Gram-Schmidt orthonormalization process, a beautiful process, and we'll go through it in just a minute. Let's just start off with some formal definitions first. So we have a set S, which is the vectors u1, u2, all the way to un, is orthogonal if any two vectors in S are orthogonal. And what that means mathematically is that u sub I dot u sub j, so u sub 1 dot u sub 3, is equal to 0. The dot product of those two vectors is equal to 0. That's the definition of orthogonality, perpendicularity, if you will. Okay, now, the set is orthonormal if each vector also has a length norm of 1. And mathematically that means that u sub I dotted with itself gives me 1. So let's just do an example. Let's take